Hello everyone. In this lecture, we are going to discuss about distress transfer functions. The references for this lectures are the Payment Analysis and Design by Huang, then Principles of Payment Design by Yoder and Witzak, and I acknowledge certain Google sources from where some photographs are taken. So the outline of this lecture would be, we will discuss about three distress models, which are the fatigue cracking, rutting and thermal cracking. So let us relook at the mechanistic empirical design approach, which we have already discussed in this course. So in a payment structure, for the design of a payment structure, the input parameters are the material properties, then the loading is traffic, and the foundation, which is the subgrade, and the climatic conditions or the various environmental conditions which affects the material properties and the behavior of the structure. So all these input parameters goes into the trial structure, and you do a mechanistic analysis, or you do a analysis of this payment structure to investigate what are the critical stresses and strains at various locations in the payment structure. Now the next key aspect in the design is that you should find out what is the amount of distress that happens, or how the distresses progress in the payment structure, or what is the amount of distress that you can expect in the payment structure. So for that you need some distress prediction models. And from those models, it should be able to find out what are the distresses that are being developed and how that accumulates, or the damage accumulates in the payment structure over the design period. Now, for the design period of say n years that you have considered, whether the accumulated damage is well within the acceptable limits, or whether the performance criteria is met or not. Accordingly, you can choose this strategy, or you have to discard the strategy and you have to modify the strategy to some other section, like you can improve the thickness of the layers, or you can go for some better quality materials. So likewise, you can redesign the strategy, and again this process has to be iterated till you find a viable design strategy. Okay. So in this course, we have already discussed how this analysis of the structure is being done to find the critical stresses and strains at various locations. Now what we are going to see is how we can predict the distresses in the payment structure, which is through the distress prediction models. So as far as bituminous payment is considered, there are a number of distresses that can happen, but the three major distresses which we consider for payment design are fatigue cracking, rutting and thermal cracking. As far as the Indian conditions are considered, we consider the first two, which are the fatigue cracking and rutting, and for other design approaches, all the three aspects are considered for design. Now, what are these distress prediction models? Now, distress prediction models, as the name suggests, is that it should be able to predict how the distresses happens in the structure. You can develop these distress functions, or you call it as distress transfer functions, from extensive field data. Okay. Now, if you use certain field data for the development of these distress functions, it cannot be directly as such used in another conditions or another situations. So if you want to use those in a different scenario, it is necessary that these these distress functions are to be calibrated. Okay. So essentially, the mechanistic empirical method or approach is set so because the aspect of empirical nature comes in this the design approach because of this distress transfer functions that we are using, which are empirical in nature. Okay. So you can say that it forms a weak link in the mechanistic empirical design method if this empirical distress functions are not appropriately chosen. So let us see the distress models one by one. So first one, or the first type of distress that are to be considered for the design is fatigue cracking. You can see a picture here with a payment surface which shows extensive cracking in the form of in the blocks or alligator cracking. Now, fatigue distress or the fatigue cracking happens in the payment structure because of repeated traffic loading, or you call it as a fatigue loading. Okay. Now the cracking that you see on the surface could be a bottom up cracking or it can be a top down cracking based on where this cracking has initiated, okay. Whether it initiates from the bottom of the bituminous layer and propagates up, you call it as a bottom up cracking, or if it starts from the top surface and propagates down, you call it as a top down cracking. Now, how to study about this fatigue cracking? Now, this cracking or the fatigue failure that happens in a payment structure doesn't happen all of a sudden. This is something which happens over a period of time. So, and this essentially happens because of the fatigue resistance or the fatigue characteristics of the bituminous layers. So, all other layers, the granular layer or the subgrade layer, we are not considering the fatigue resistance of these materials because they have very negligible fatigue resistance as compared to the top bituminous layer, okay. So, in order to study this fatigue behavior or the fatigue characteristics or the fatigue life of a bituminous pavement, essentially you can have three approaches. The first one is that you will see what are the relationship between the repeated stresses and strains in a laboratory test on a bituminous material and its relation to the number of repetitions or number of load cycles to failure, okay. So, what you call it as a Miner's law of cumulative damage approach. You see how each load application damages this material and this can be accumulated to find out how this will perform in the field, okay. So, this approach is called a Miner's law, and the second one is a energy dissipation approach, wherein what you see is that or what you try to find out is that at every load cycle, how the energy get dissipated. So, it is found that the energy dissipation actually depletes from one cycle to another. So, based on the energy dissipation on this specimen, you can measure how this, how the fatigue life of this material is going to progress or how the fatigue life is going to happen. Now, the third one is called the fracture approach. You can use the fracture mechanics to study this initiation and progression of cracks. Now, what is this initiation and progression of crack? See, this as I said, this fatigue cracking or the damage due to fatigue, repeated fatigue loading does not happen all of a sudden. See, your bituminous mixture is having certain voids. Now, these voids, when they become interconnected, they can have micro cracking networks. So, there will be small cracks that will be developed, which essentially are cracks due to the this fatigue loading, and they form a micro cracking network. Then can cause a decrease in the modulus value of the material, okay. In order to study this aspect or the initiation of a cracking in a bituminous mixture, you can use some failure damage theories, okay. Whereas, once it starts micro cracking, there could be possibility that all these crackings get coalescence, or the coalescence of the cracking can happen. That can, so this after certain level of micro cracking, and that can form to macro cracks, okay. Now, this macro cracks propagates in the material, like as I said, it can propagate from one point to the other. So, in order to study this propagation, you can use fracture mechanics concepts, okay. So, these are the two phases of a fatigue cracking in a material. Now, in order to consider this fatigue cracking for design, the fatigue distress is quantified in terms of the area of cracking that you see on the surface, and this is related to the number of repetitions of loads to failure, okay. Now, in order to see what is the number of repetitions to failure, that number of load repetitions is actually related to the tensile strain at the bottom of the bottommost bituminous layer. So, this is a typical cross section of a bituminous pavement with granular base and granular subbase. Taken from IRC 37 2018. As you can see here, the bottom layer is subgrade and the next layers are granular layers, which is your subbase and the base, and the top layers are the bituminous layers. You have two layers here. The bottom is here termed as a fatigue resistant layer and the top one is termed as a rot resistant layer. So, essentially, due to repeated loading on such pavements, it is understood that the tensile strain at the bottom of the bituminous layer, when when that exceeds, or the tensile stresses exceeds, it will start cracking from the bottom, and the bottom up cracking is essentially, or the major mode of type of cracking in the case of bituminous pavement. Okay, so it is recommended to have a fatigue resistant layer as the bottom layer of the bituminous layers if there are 2 layers of bitumen. Now, first of all, before going into the pavement structure, let us consider the bituminous material. So, we do fatigue cracking analysis, or the fatigue characterization of this bituminous mixtures. There are various ways by which you do that, and one can always refer to our previous NPTEL course on mechanical characterization of bituminous materials, where we have discussed in detail how this fatigue characterization of bituminous materials is carried out. Now, from such laboratory investigations, it is seen that there is a strong relationship between the tensile strain and the fatigue life. Okay, so this relationship actually can be extended to the pavement structure. So, this is what is led to the development of fatigue cracking models or the distress transfer models. Okay, so you can see here there is a picture shown which is a typical relationship between the strain and the number of repetitions to failure on a bituminous mixture in the laboratory. So, you can see that there are 2 mixes considered here. One is a mix with a low stiffness and the other is a mix with a high stiffness. And you see that the tensile strains that happen in the material is low for a high stiffness material and high for a low stiffness material. And also, if the strains reduces, as you see here, as the strain reduces, the your number of repetitions to failure will be more. Okay, so it will take large number of load repetitions till it reaches a failure state. So, based on such laboratory fatigue test, you can have expressions as written here, where NF is the number of repetitions to certain failure by fatigue, is C1 into epsilon t raised to minus F2 into E1 raised to minus F3. Okay, now so where this F2, F3 are material parameters or coefficients that are that you can get from the laboratory test, the fatigue test on this mixtures, and C1 is again a coefficient. Now, since this is a general form of fatigue equation for bituminous mixtures, when you consider the bituminous layer in the pavement structure, you can have a similar structure for the prediction of fatigue. Okay, fatigue life or fatigue. So, the similar expression can be used wherein NF will represents the number of repetitions or load repetitions to failure of the pavement structure by fatigue, and the C1 can be replaced with another factor which is F1, which will indicate the shift from the laboratory investigation to the field investigation, okay, or the payments, or I'll say that is actually the shift from the fatigue response of the mixture in the laboratory to the fatigue response of the pavement layers, or the top layer, or the pavement structure as a whole in the field. Okay, but one have to note that this F1 has to be much greater than C1, because the V loads, if you consider the pavement structure, it will take more number of load repetitions, because all the V loads are not going to act at the same point in the pavement structure, and also there will be rest periods between 2 loads. So, it is not necessary that a small number of load repetitions will bring it to a failure. So, and also in the case of thicker pavements, there will be a large amount of time that may require from the crack to propagate from one location of its initiation to the surface of the pavement. Okay, essentially the distresses will be measured as you see on top of the pavement structure, right? So, F1 will be a factor which will be much greater than the C1 factor that is estimated from the laboratory. Okay, so sometimes in certain studies, say for example by PEL, this effect of the material modulus is neglected because it is found that the coefficient corresponding to the material modulus here, that is this F3 coefficient, is less compared to F2, that is the influence of material modulus on this expression is less, so which can be neglected. So, PEL has given a general equation as NF is equal to K1 into 1 by epsilon T raised to K2. That is, you have removed the minus and put epsilon t in the denominator. That's all. That's a difference. So here also K1 and K2 are the coefficients, where K2 is the constant that is related to the fatigue characteristics of the bituminous mix in the laboratory, and where K1 is that parameter that will indicate what is the shift from the laboratory performance of the mix to the fatigue failure values in the field. Okay. So, as I said, this is the general expression F1 epsilon t raised to minus F2, that is, instead of writing epsilon 1 by epsilon t, you can take it as epsilon t raised to minus K2 or F2. So, in general, it is written as F1 and F2, the coefficients are written like that. Now, the idea is to get these coefficients from extensive laboratory as well as field studies, because as I said, F2 can be estimated from the field, from the laboratory investigations of the various bituminous mixes, and that has to be correlated to the field performance. Then only you can arrive at this distress transfer functions. So, various studies has been conducted by different agencies, and some of these are written here. So, you can see that the Illinois Department of Transportation by Thompson in 87 has given an equation as 5 into 10 raised to minus 6 epsilon t raised to minus 3. Okay. Whereas TRRL has given the expression as with an F1 value of 1.66 into 10 raised to minus 10, and F2 takes a value of minus 4.32 or 4.32, and the Belgian Road Research Center has given a value with F1 as 4.92 into 10 raised to minus 14, and F2 is minus 4.76. Okay. So, what you have to note here is that the F2 factor, which is from the lab test on fatigue test on lab specimens, the parameter or the coefficients doesn't vary much from when that is done at different laboratories. You see that the coefficients has varies from like 3 to 5 or something, whereas in the case of the F1 coefficient, you see that in these three models itself, you see that it varies from 10 raised to minus 6 to 10 raised to minus 14. So, this highlights the importance that this, whenever you want to use this fatigue cracking models, it is necessary that it is well calibrated and this field performance is properly captured through this F1 parameter. Okay. So, again, this is, as I said, certain models have neglected the influence of E, the material modulus, but certain have considered that as well. So, again, the general expression is written here with K1 1 by epsilon t raised to K2 and 1 by E raised to B. The coefficient is named as B by Finn et al. Where E is the stiffness of that bituminous mixture or hot mix asphalt as written here, HMA, and K1, K2 and B are the regression coefficients. Now, if you look at these coefficients, what are the parameter or what are the factors on which these coefficients will depend on? The first one is, of course, epsilon t raised to K2. So, that is for the bituminous mixture. So, essentially, what is the type of the bituminous mixture? What are its volumetric properties? What is the stiffness of this mixture? What is the kind of binder that you have used? All these aspects will dictate what is the K2 value, whereas when it comes to K1, K2 as well as the value B, because that is related to the modulus of the material. Now, when it comes to K1, it will depend on various parameters like the bituminous. In addition to these factors, it will depend upon various parameters like the bituminous layer thickness, what is the axial load that is coming, what are the field conditions, environmental conditions and so on. Okay. So, all these models are developed based on the same concept or the same basic model. So, Elliott and Thompson has given, they have conducted extensive studies on the ASHO road test. So, the data that American Association of State Highway Official Road Test data, the like deflection based data and also the performance based data from this road test has been utilized, and they have represented the cracking model in terms of a logarithmic equation like log n is equal to 2.4 and minus 3.16 log epsilon minus 1.4 log E. So, there is one form that they have developed. So, next is the shell fatigue prediction equation, which is used in the Osterud's payment design. As you see here, again, the allowable number of load repetitions for fatigue is given in terms of various factors like VB, there is an S mix, there is mu epsilon, and there is a term m here. So essentially all these terms like M, mu, VB, SMIS, etc. corresponds to the type of the bituminous mixture, where VB is the percentage volume of bitumen on the mixture, then S-mix is the flexural stiffness of the mixture in megapascal. So the various models actually differ the way in which the material modulus is incorporated in the model. Like here it is a flexural stiffness is used, somewhere it is the elastic modulus of the material is being used, and some studies have used the dynamic modulus of the material. So based on the type of the way in which the material is characterized, they have developed the equations. Okay. Now mu epsilon is the strain level that is chosen for the estimation of the properties of the material, and M, the term M here is defined as 4.84 into VFB minus 0.69, where VFB is the voids filled with bitumen, which is again given by VB by VB plus VA, where VA is the air voids and so on. So what you see here is that it is essentially the material parameters that goes in the equation, and these coefficients that you have see here like 6918, those are the coefficients which have obtained from the field studies. Okay. Now, Asphalt Institute again considers the general equation itself as the predictive equation or the fatigue prediction equation, where NF is equal to F1 epsilon T raised to minus F2 into E1 raised to minus F3, which we have already discussed, where NF is the allowable number of load repetitions for fatigue in the pavement structure, and epsilon T is the tensile strain that now how do you get this tensile strain in the pavement structure? For a particular load application, you can find what is the strain or the critical strain at the bottom of the bituminous layer, that forms the tensile strain here, and E1 is the modulus of the bituminous mixture, and K1, K2, K3 are the regression coefficients, where K2 and K3 are the regression coefficients, and K1 essentially represents the laboratory to field adjustment factor. Okay. Asphalt Institute has given an NF equation as written here, and the shell equation is also written here. You can see the coefficients, they vary slightly. Like in Asphalt Institute, the F1, F2, F3 are of the order of 0.07, minus 3.2 and 0.85, and you can see what are the corresponding values in the shell equation. Now, I said that NF is the number of repetitions to failure. Now, the failure criteria has to be set, right? So, in this, so every design approach will choose a certain criteria as the failure criteria. So, as far as this Asphalt Institute method is concerned, 20% of the cracked area, or if the area of the pavement structure, if 20% is cracked, that is assumed to be a failure criteria. Okay. The fatigue damage equations are provided in the MEPDG, the Mechanistic-Empirical Pavement Design Guide. Again, that also is in the similar lines, but there are certain calibration factors which are incorporated. So, you can see the general form which is given in the MEPDG, which is NF is equal to K1 beta 1 by epsilon T K2 raised to K2 beta 2 and 1 by E1 raised to K3 beta 3. So, here epsilon T, E1 and all the definition are same as what we have already discussed. Now, in order to get the epsilon T, you have to do the analysis of the pavement structure. You can do a layered elastic analysis and find what is the critical epsilon T at the bottom of the bottommost bituminous layer. And K1, K2 and K3, sorry, this is K2 and K3. So, K1, K2 and K3 are called material calibration factors. Now, suppose you are using certain material or the different classes of materials that you use. For those materials, you can do the extensive laboratory investigation to arrive at these parameters, and beta 1, beta 2, beta 3 are the calibration factors. So, what you see in this MEPDG model is that there is not just one calibration factor which is given for field calibration or the transferring from the lab to the field. There is a calibration factor which is given along with all the coefficients. So, if somebody wants to use this information, they can use the study, the data that is available for the study from the study conducted at that particular location or that particular region to develop or to arrive at these fatigue damage equations. And these are some of the default values which are given in MEPDG. So that is K1.0075, K2 3.9749 and so on. Let us see how this fatigue is considered in the IRC 37 2018 or the Indian Standard Specifications. So here in IRC 37, the failure condition is considered as an area of fatigue crack of 20% of more, as in the case of the Asphalt Institute. So similar 20% cracking is considered as failure. Now, the distress transfer function essentially gives you the equivalent number of standard axle load repetitions that can be served on the pavement before the critical condition of cracked surface being 20% or more occurs. So, number of repetitions to failure by the surface being cracked by 20% is what is given as the distress transfer function. Okay. Now, in IRC 37, the distress transfer functions are prepared at two reliability levels, and the data for this is being used from the performance study, the BBD studies, etc., that are conducted on a number of road stretches as per the R6, R19, R56 scheme and all of the Ministry of Road Transport and Highways. So, this extensive data has been used to arrive at the distress transfer functions. So, as you see here, these are the two distress transfer equations for fatigue at 80% reliability, and the other one is for 90% reliability. Now, what are these reliability aspects that will be discussed by Professor Nivita in her lecture in this course. So, let us see what are the parameters here or what are the coefficients here in this fatigue equation. You see that NF is given as a coefficient into C, and 1 by epsilon t raised to a coefficient and 1 by m rm raised to a coefficient. Okay. Now, what is this C? C is represented as 10 raised to m, where m is equal to 4.84 VBE by VA plus VBE minus 0.69. Okay. So, essentially this C and m relates to the characteristics of the bituminous mixture that is we have considered, okay, or MRM here is the resilient modulus in megapascal of the bituminous mix in the bottom bituminous layer, and which is selected as per the recommendations provided in the IRC 37 guidelines. So, you have to find the resilient modulus of the material that you are using at the bottom bituminous layer, and that resilient modulus goes in here, which is denoted as MRM. And for the mix, what is the VBE, which is the percentage of effective bind bitumen in the mix. Again, the mix you have to consider is the bottom bituminous layer, and VA is the percentage of air voids in the bottom bituminous layer. So, use those values to get M and C, which is 10 raised to M, and then when that goes in here, you will get how many is the number of repetitions. Okay. So, NF is essentially the number of repetitions to failure, failure being defined as 20% of area being cracked, or you call it as a fatigue, or you call it as a fatigue life of the bituminous layer. Now, what is the loading that you have to consider? You have to consider the equivalent standard axle load of 80 kilonewton, that is a single axle dual wheel that we have already discussed in traffic. Okay. Now, this damage that it accumulates over a period of time due to fatigue or the fatigue cracking damage can be expressed in or explained using the minus cumulative damage concept. Okay. So, this concept can be used either to predict the fatigue cracking or determine the damage that has already occurred. Now, what is this minus hypothesis? It actually gives you a relative, it represents a relative damage factor. Now, what it says is the portion of useful fatigue life that is used by a number of repetitions of load cycles or stress cycles at one particular stress level is actually proportional to the total number of cycles in the fatigue life if that was the only stress level that is being applied up to that in that payment structure. That is, say for example, you have a stress level of S1, okay, or S, and the small ni represents the number of load applications of that stress level in a time I, okay, and suppose only this stress level is being applied, Capital Ni represents the total number of repetitions that can be applied before it comes to a failure. Okay. Then the minus hypothesis say that this Ni is actually proportional to capital Ni. Like or you can say that the damage that happens to, or the proportion of damage that happens till I time can be given as di is equal to Ni divided by Ni. Now, okay, so this gives you what is the proportion of the fatigue life that has been used by this particular stress level. Okay. Now, similarly, suppose you have multiple stress or loadings of multiple stress levels, you can see that, say for example, in this first one, this is S1 is the stress level and second one S2 is the stress level, and at each stress level you have a different number of applications. The N1 is the number of application at stress level S1, N2 is the number of application at stress level S2 and so on. Then for each stress level you should know what is the total number of applications of that alone which can lead to a failure. Like for example, if S1 it can be capital N1 and for N2 it can be capital N2 and so on. Then the total damage that has been accumulated, if you had different stresses being applied, that can be written as D is equal to sigma I is equal to 1 to K of NISI divided by capital NISI. So, I hope the concept is clear. So, small ni by capital Ni essentially gives you the proportion of the damage that has been accumulated because of the first, say for example, you have K number of stress levels. So, the first stress level, okay. So, the SI is multiplied so that you can see that it is for different stress levels, okay. So, Minor's rule essentially assumes that the damage done by each stress repetition at a given stress level is equal. Like if you have one stress level S1, if it is applied for the first time or if it is applied for the 10th time, the damage caused at each of these applications remains the same. Okay. So, this hypothesis can be used to sum up what is the damage that is being happened because of each one of these load applications or each of this set of load applications. And then the amount of damage can be expressed as a damage ratio, where damage ratio is represented as the predicted number of repetitions to failure divided by the allowable number of repetitions. Now, when this damage ratio reaches 1, you can say that the failure has occurred, okay, because the predicted number of repetitions reaches the allowable number of repetitions. Now, how the damage is being accumulated is given by the Minor's rule, okay. Now, suppose in the analysis you are using mean values of the various parameters are used for design, then a damage ratio of 1 will indicate that the probability of failure is 50%, okay, because the 50% of the area will have reached fatigue cracking, so that the damage has reached. Now, what you can do is that you can assume a log normal distribution for the damage ratio, and the probability for failure or the probability for fatigue cracking can be computed, and that can be checked with the field performance. So, this is a damage accumulation method by which you can see whether how the payment structure will perform. Now, as far as IRC fatigue cracking equations are considered, we are not using this damage approach or the Minor's approach as such, because you are just comparing what is the number of repetitions to failure as one, you get it from the one distress equations. So, for n number of design years, you find out whether the design is safe or not. But there is the cement treated base or sub bases that are considered in IRC cross sections. Various cross sections are suggested in IRC. As you see here, the bottom granular layers are now replaced with a cement treated base or sub base layer. Now, when it is cement treated, this becomes a stiffer material, which the chances of fatigue failure of this material increases as compared to a granular material. So, it is necessary that the fatigue response of this material or this layer also has to be investigated. Now, for that you have to see the tensile strain at the bottom of the cement treated base layer, okay. So, for the cement treated base, this is the IRC 37 model that has been given, where log 10 NFI is equal to 0.972 sigma T by M rupture, M rup divided by 0.0825, where NFI gives the fatigue life of the cement treated base material, which is the maximum number of axial load repetitions of the ith load class that the cement treated subbase or the base material can sustain. And it is related to the stress ratio, wherein sigma T represents the tensile strain at the bottom of the CTB layer for the given axial loads that you can determine using the layered elastic analysis, and MREP represents the material modulus, or in terms of the flexural strength of the cementitious base, that is a 28-day flexural strength has to be used. Now this essentially gives you the number of repetitions or the fatigue life that has been utilized till by an ith class of a load class, okay, ith load class. Now the cumulative fatigue damage as per the Miner's approach caused by the different repetitions of the axial loads for different categories and different magnitudes which are expected to be applied on the pavement during the design period can be calculated as sigma of Ni by capital N Fi or Ni, okay. So this is your Miner's approach, okay. So here Ni is the expected repetitions of the axial load during the design life period, and NFI is the fatigue life or the maximum number of load repetitions on the CTB layer which it would sustain if only this particular vehicle class of class I is available, is applied on the structure, okay. Now Ni by NFI you keep on adding for each class of each class type. So for each class you know what is the capital NFI for that particular class and the number of load repetitions for that particular class that has happened, so that the damage, relative damage by each class can be computed, and add them together to find what is the total damage that has happened, and then see what is this cumulative fatigue damage, and if this cumulative fatigue damage is less than 1, which means that the design is acceptable, that is the damage has not exceeded. But if this cumulative fatigue damage is exceeds 1, then the pavement section has to be redesigned. So in the design of flexible pavements with this cement treated base layers, it is recommended that this approach has to be used to check whether the CTB layer is okay or not, or the design is appropriate or not. Okay, so moving on, just wanted to iterate what is reinforce the aspect that there is a need for calibration when you want to use these fatigue cracking models. Unless it is being developed based on extensive data that is applicable to that particular field condition where you are going to use this models. So the models are regression equations with a number of constants, so which are to be calibrated so that a best fit between the predicted distresses and the actual field values can be obtained. Now, the problem is that if you have a regression equation or an empirical equation, all the factors that are causative factors that contribute to the distress prediction or the formation of the distress may not have been incorporated in that equation, because it's basically an empirical equation. So, if those unaccounted factors are same for in the new situation scenario where you are going to use this equation is unchanged, it remains the same, then the models can be used with confidence. But if these unaccounted factors are different for the new conditions where you are going to use this, then it is always necessary that a recalibration of this model is done.